Hi, everyone. It's a pleasure to be here today. My name is Sam Stanwyck. I'm the product manager for quantum computing software at NVIDIA. And today I'm going to talk about how by simulating quantum circuits on GPUs, you can do fundamental research and actually help answer some of the most important questions in quantum computing at performance and scale that's not possible on quantum hardware yet. And so I'm also going to introduce a new NVIDIA software product called cuQuantum, which is meant to dramatically accelerate these simulations and extend them to new regimes. So first I'm going to talk a little bit about the background of kind of where we see the field today and how classical high-performance computing fits. So there's, of course, been a ton of exciting progress in quantum hardware in the past decade, going from one or a couple of qubits a decade ago to systems with tens of qubits or maybe over 100 qubits, just starting to cross this quantum supremacy barrier where a quantum computer can do something a classical computer can't. And of course, maybe not necessarily on a useful problem, but still a really important milestone. But here in general, we're still very limited on quantum processors by both scale and noise. Of course, because errors accumulate in a quantum circuit. In practice, you often can't do much of value with actual quantum processors. And sort of way up on the other end is the fault-tolerant regime, where we get to enough physical qubits, maybe 1 million, as well as improve error rates low enough to actually do error correction to a useful degree, that we can start to talk about getting to proven exponential speedups with the quantum computer. And so when we get here is a big open question, of course, but I don't think it's unreasonable to say this is at least 5 or 10 years away. And so in between, we have this really interesting period, the noisy intermediate scale quantum era, where quantum computers are scaling up and error rates are improving. And it's an open question when and where we can see quantum advantage. And I'm going to say here that quantum circuit simulation is an incredibly useful tool to both help drive the field forward in this era and maximize the value that we can get from quantum computing before we get to fault tolerance, especially in enterprise. And so, of course, hardware progress, scaling up systems and reducing error rates is incredibly important. But at NVIDIA, we're also thinking about how we can use some of the tools we already have to answer some of the most important questions now. So while quantum processors are improving, can we simulate quantum circuits much faster and at much larger scales, and maybe get a better understanding of things like which quantum algorithms we expect to see a quantum advantage for which problems, what are the requirements we expect in terms of both qubit scale and error rates, and maybe which architectures are best suited to which problems. And so, zoomed in, that might look like answering questions about which algorithms are sensitive to which certain types of noise, or which tweaks to an algorithm reduce the resources needed, or what connectivity or compilation strategy reduces the resources required for a certain circuit. And it turns out that answering questions like this with quantum circuit simulation is a really good fit for GPUs. And the plan is that in the same way that GPUs and GPU-accelerated libraries have made such a world of difference for AI, we can hope to do the same for quantum computing research. So in reality, the picture is somewhat more complicated than this up here, but there are basically 2 main types of quantum circuit simulation approaches. So there's state vector simulation, which you can think of as kind of the brute force method. So you hold the entire state as a vector of size 2 to the n and update it every time step. So the advantage here is that, first of all, you can simulate very deep circuits. It's very easy to handle different types of noise models. And you just generally have a lot of flexibility. So with full access to the state at any time, you can do things like mid-circuit measurements, for example. And of course, the limitation here is like the hard requirements of memory. So on a single CPU or GPU, this usually means you top out at somewhere in the 30s of qubits that you can actually simulate. And even on a supercomputer, it's very hard to even get to 50 qubits. And so an alternative approach is what's called tensor network simulation. And here you essentially model the entire quantum circuit as a tensor network, do some clever optimization to calculate the optimal path for contraction of that network, and then contract the tensors one by one. And so this gets around the hard exponential memory limit, and how many qubits you can actually simulate here really depends on each particular circuit. And it turns out that for many of the key quantum algorithms that people are looking at for near-term quantum advantage, they tend to be shallower, they tend to be lower entanglement, and so the tensor network representation is not that complicated, and so it lends itself really well to doing this, and you can actually scale up to hundreds or thousands of qubits for these circuits, which is pretty exciting. And I'll talk a little bit more about that later. And so now I'm going to get into the details of cuQuantum, which is our SDK for supporting quantum circuit simulation. And so it's first of all very important to understand what cuQuantum is and what it isn't. So it is an SDK of optimized libraries and tools for accelerating quantum circuit simulation. So it's not itself a framework like Cirq or Qiskit, or even a simulator like QSIM within Cirq or Air within Qiskit. It's meant to flexibly plug in as a backend to any simulator and accelerate it on GPUs. And so in cuQuantum, we have a library for accelerating both state vector and tensor network simulation. And so I'm not going to get super into the details of what cuQuantum can do in this talk, but I highly recommend Haroon Bayraktar, who's our director of engineering for this at NVIDIA, his talk on Thursday, which will be a much deeper dive. So what is cuQuantum intended for? It's meant to accelerate a broad range of quantum circuit simulators on GPUs. It's very low level, at the level of just multiplying matrices and vectors. So it sort of seamlessly handles perfect or noisy qubits equally well. And the hope is that it will enable algorithms research at scale and performance not possible on quantum hardware, certainly, or unaccelerated simulators today. So we're in open beta now. So QStateVec is actually public. We're planning on a second release in a couple weeks, which will make QTensorNet public. But QStateVec can be downloaded from NVIDIA.com today. And we're actually already making progress on integration with frameworks. So our integration with Cirq is public. You can now use cuQuantum through Cirq. We'll be supporting Qiskit starting in December. And I'm excited to announce that we're also going to be supporting PennyLane, the framework for quantum machine learning from Xanadu, starting in January. And so going forward, we intend to keep helping folks integrate cuQuantum as a backend and accelerate all the simulators in the ecosystem. So what kind of performance gain can you expect? So we've done some early benchmarking on our single GPU version of QStateVec. And so on the left here are quantum Fourier transform, Shor's algorithm, and the random quantum circuits from the Sycamore supremacy experiment at depth 14. And here the comparison is a single A100 GPU versus a single 64-core CPU. And we're plotting speed up. And so as you get into the 20s or 30s of qubits, we start to go towards a 10 to 20x speed up GPU to CPU. We've also tested this out for VQE of a few different molecules, lithium hydride up to ethylene. And it's a similar story. Like as you get to a larger molecule, like into the 20s of qubits, you get towards a 20x speed up. And so these are GPU to CPU comparisons, but cuQuantum also compares very well to other GPU accelerated simulator libraries. And so for QTensorNet, the analysis is a bit more involved. So for a tensor network simulation, there are basically two steps. So there's the path finding, where you run some optimizer to find the optimal path, and the contraction itself. And so here we have data about both. And so the way to read this is all of these are contraction speedups of QTensorNet relative to cuPy, which is a GPU-accelerated library, but not specialized for tensor networks. And so the green bars are where QTensorNet also calculates the path. The yellow bars are where Cotengra, which is an open source framework from Garnet Chan and Johnny Gray at Caltech, calculates the path. And the gray bars are where OptEinsum, which is kind of the default thing that people can use through NumPy, calculates the path. And for the QTensorNet and Cotengra calculated paths, we see, again, a 10 to 20x speed up for the contraction for QTensorNet versus cuPy. Of course, very problem dependent. The other big piece of data here is the quality of the path finding itself. So here, the way to look at that is to compare the bars within a problem. So QTensorNet is the green bars is beating OptEinsum, the gray bars for every problem, very problem dependent. With QTensorNet versus Cotengra, they're very similar. So Cotengra is better on some problems. QTensorNet is better on others. I'll say that QTensorNet generally runs about an order of magnitude faster than Cotengra now to get these paths. And furthermore, these are results from our first release. And so for the release in December, we're adding some further optimizations. And so we expect QTensorNet pathfinding to still be faster and also beat Cotengra on all problems. And so this is as much as I'm going to get into cuQuantum single GPU performance now. And again, I'll point you to Haroon's talk on Thursday if you want to find out more. And so where we're going next for cuQuantum is multi-GPU. So in January, we'll be releasing what we're calling the DGX Quantum Appliance. And so what that is a container with a Circ front end, the QSIM simulator within Circ, and then accelerated by cuQuantum, which can just be pulled from NGC, which is our container website. And so this is a complete simulation solution, and it'll be optimized for our DGX A100 system, which is 8 GPUs. And so we've done some early benchmarking on this with really exciting results. And so what I'm plotting here is the same 3 problems from QStatefect before, Shor's, the quantum Fourier transform, and Sycamore. But now the speed up over a dual CPU solution as a function of the number of GPUs. And what we see is really nice strong scaling. So as you double the number of GPUs for the same problem, you want the problem time to half if you're doing things perfectly. And so that's about what we're seeing. The speed up is almost doubling, up to a 50 to 90x speed up using 8 GPUs. And so we're really excited about applications of this. There are some quantum groups that are already starting to take advantage or thinking about starting to take advantage. And so I'll point you to Pascal's talk, Neutral Atoms, the next leap in quantum computing, tomorrow afternoon for just one example. And so now I'm going to turn to an example of how cuQuantum running on a GPU supercomputer can tackle key problems at a new scale, so namely simulating max cut. And so if you're not familiar, max cut is a graph optimization problem that basically asks for the line creating the optimal cut of a graph. partitioning it into two groups. And so it's an NP-complete problem. It has a broad array of applications, including areas like clustering, network design, and statistical physics. It's also been a subject of a lot of interest in quantum computing over the years because it's one of the first algorithms where we've really looked at variational hybrid classical quantum algorithms as a potential early candidate for quantum advantage. So primarily QAOA, which was introduced in 2014, solves max cut and is one of the most popular quantum algorithms today. And several groups have actually done this on hardware, including one example which I show here from Rigetti. This was in 2017, where they tackled max cut on their 19-qubit quantum processor. And so it turns out that these variational quantum algorithms to solve max cut are a really, really good fit for tensor networks. So the level of entanglement is relatively low. The circuits are relatively shallow, which means that you can often scale this really well with a tensor network representation. And there has been several papers in recent years, ILIS-3 from USC, Alibaba, and Argonne, where they all use tensor networks to simulate max cut at scales up to hundreds of qubits. So this summer, a team from NVIDIA research looked at this and proposed a novel variational quantum algorithm where they encode the circuit into a 1D tensor, or encode the graph into a 1D tensor ring, and actually encode separate vertices of the max cut graph into the x and the z bases of the same qubit separately. Which effectively has the number of qubits needed to solve the same problem. And so running this with an early version of cuQuantum, they were actually able to simulate a 512 vertex system, so 256 actual qubits on a single A100 GPU. And so here in the lower right, you see the convergence to the optimal solution versus epoch for 8 qubits, 100 qubits, and 500, or sorry, 8 vertices, 100 vertices, and 512 vertices, compared to dotted line plots for 8 and 100 for VQE. So this does seem to be an improvement over standard methods, and it's exciting that we're able to do so well on a single GPU. And so if you're interested to find out more, the paper is on the archive, and the code is now on GitHub. And so in the last couple months, we tried extending this to a supercomputer and got some pretty interesting results. So we were actually able to simulate a 1,688 qubit problem, so 3,375 vertices with 97% accuracy, and actually tried all the way up to 10,000 vertices, so 5,000 qubits. And there did okay, but saw the accuracy kind of start to fall off. And so this is really exciting because, first of all, it's more than an order of magnitude what's been done in simulation before, not to mention multiple orders of magnitude beyond what can be done on quantum hardware today, and actually really getting towards the scales where we can start talking about things that are relevant for quantum advantage. So you could imagine pushing to larger scales and seeing where this the classical simulation really starts to really not converge, or using this to simulate noisy qubits, or simulating tweaks to the algorithm to see what kind of performance improvements you can get. And so we think this is really interesting to keep following up on. And more broadly, these tools and this hardware generalize beyond max cut to kind of a whole host of problems like this across a vast base of applications. And so we're really excited going forward to work with the rest of the community and start applying this to new problems and new use cases. So what to expect next? I've already talked about a little of this. So cuQuantum is now public. It can be downloaded from NVIDIA.com today. We're releasing a second beta in a couple weeks, which will add more APIs. It will make cuTensorNet public and add Python support, as well as Qiskit integration. And then an NGC container will be made available, which will be a full quantum circuit simulation solution with Circ and QSIM, accelerated by Q2B, running on the multi-GPU DGX A100. And then beyond that, integration with more frameworks, additional APIs and kernels to support use cases from the community, and scaling this up to multi-node. So just in summary, we think quantum circuit simulation is going to be a vital tool for answering some of the most important questions in quantum computing. We're introducing cuQuantum as a way to accelerate that, improve performance and scale, and have an example already about how cuQuantum plus a supercomputer can enable a new scale of quantum algorithms research. So with that, I'll end and take questions. Oh, so these are solved classically. Like we're not yet approaching. I think the largest problem solved with classical methods is like up to like 90,000 vertices. So there's just a library with you know these problems and the right answer for the optimal cut. From us or for like pure classical, not simulating quantum? That I don't know. Yeah.
But can I ask what are the biggest challenges in simulating quantum computing, like noise handling or those kind of things?
So because our libraries are so low level, you know, it's at the level of a matrix vector multiplication. So it really doesn't know anything about the noise in the circuit. So, you know, you can take like the noise models in Circ and Qiskit, and it just handles those seamlessly. You know, I'd say the biggest challenge is scaling. So, you know, obviously with state vector, you're climbing an exponentially steeper hill, and so, you know, it's, you know, what can you do then with in the 30s or 40s of qubits? With tensor networks, it scales really well for certain problems, but it's very problem dependent and very depth dependent. So it depends on the size of the maximum intermediate tensor you generate. And so we're kind of working hard to optimize that to scale to multi-GPU and multi-node so we can do much bigger problems. Sorry, I couldn't hear the end of the question. Yeah.
Are you intending to provide additional support for exploration of error correction fault tolerance at these scales?
Yes, yeah, definitely. So maybe to the first part, you know, I'll say that there are caveats, of course. So, you know, this is a 1D tensor ring, so, you know, multiple dimensional, like higher connectivities are harder to simulate classically. But yes, like we're at the scales where simulating error correction is very relevant and interesting, and definitely interested in helping with that. All right, well, thank you very much.